In this video, I will present topics 7.3, 7.4, and 7.6, thermal inversion, atmospheric carbon dioxide and particulates, and reduction of air pollutants. Because of atmospheric circulation, which is influenced by the rotation of the Earth, long-term climate patterns, and short-term weather conditions, any pollutant suspended within it is free to migrate whichever way the wind blows. It's important to remember that the atmosphere, like Earth's oceans, is a prime example of a commons. The pollutants released into it in one part of the globe will not remain there. Some places on Earth, because of the climate and also topography, are more susceptible to the harmful effects of pollution than other places. The presence and movement of particulate matter in the atmosphere is especially influenced by weather and climate. You may recall from an earlier unit that temperature decreases in the atmosphere as altitude increases. Since the atmosphere warms from the surface of the Earth up, air masses become less dense and begin to rise. Pollutants that are suspended in that air mass are also carried up as the air rises. Under normal conditions, those pollutants are free to diffuse and be carried away. But sometimes a relatively warm layer of air at a mid-altitude covers a layer of cooler, more dense air beneath it. This is referred to as a thermal inversion. The warm inversion layer effectively traps pollutants beneath it. Thermal inversions are especially common in densely populated areas and occur more readily in places where geologic barriers, such as hill or mountain ranges, contribute to the trapping of air. This photographic comparison of the city of Stuttgart, Germany, clearly illustrates the effects of a thermal inversion. In these two images of Los Angeles and Almaty, Kazakhstan, the delineation between the cooler, polluted air and the warmer, cleaner air above is quite distinct. This picture shows how smoke from a small fire in a town in Scotland is trapped beneath the inversion layer. Carbon dioxide is one of the gaseous components of the carbon cycle. It is naturally released into the atmosphere from organisms as they respire, as well as the decomposition process that breaks down dead organisms. The oceans can both absorb carbon dioxide from the atmosphere as it dissolves into water and release it back into the atmosphere via outgassing. Naturally occurring forest fires and volcanic eruptions are also responsible for carbon dioxide in the air. Of course, our influence on the carbon cycle primarily comes in the form of fossil fuel combustion that results in the excess release of sequestered carbon, driving up the net concentration of carbon dioxide in the atmosphere. Unlike other forms of pollution, particulate matter has a significant naturally occurring contributing factor. You may recall from the previous video that particulate pollution can be classified by size, PM10 and PM2.5. Particulates also vary by type. Some are solid or liquid, and others are biological, such as mold spores, the waste of dust mites, and pollen. Exposure to the smaller of the two particulates, PM2.5, contributes to the death of up to around 4 million people annually and ranks as the 6th leading risk factor for premature death worldwide. And as anyone with asthma or allergies can attest, particulates are more than just a nuisance, since not only does it decrease the quality of life, but they can also make breathing dangerously difficult. Volcanic eruptions and forest fires are a couple of the leading sources of naturally occurring pollutants. Severe weather events can lead to massive amounts of particulates being picked up and transported, such as this dust storm in Phoenix, Arizona. They can even become so large that satellites in orbit can observe them, like this one off the coast of Namibia and South Africa. Legislation such as the Clean Air Act and its subsequent amendments has resulted in the adoption of policies and regulations aimed at reducing the emissions of air pollutants. In most developed nations, regulations have been effective in reducing pollutants such as carbon monoxide, sulfur dioxide, nitrogen oxides, as well as particulate matter. In order to meet the demands of regulations, systems or devices that are designed to capture or neutralize pollutants are installed on factories, power plants, and vehicles. Many regulations also carry the potential for penalties in the event that businesses fail to adhere to them. Although the enforcement of such penalties fluctuates with changing government administrations, they can involve hefty fines, prison time, or both. As with other topics in environmental science, there are advantages and disadvantages to consider. Regulations directly increase the cost of operation for a business. This increased cost is generally passed on to the consumer in the form of more expensive goods and services. However, the long-term benefits of regulations, including economic ones, typically exceed the costs associated with them. For example, having cleaner air translates into better health and therefore less need for not only expensive medical attention, but also reduces premature mortality. In the world, there are nearly 1.5 billion vehicles, and this includes over 270 million vehicles in the US alone. The fuels, like gasoline and diesel, that are used to power automobiles are volatile organic compounds that readily evaporate and escape into the atmosphere. In order to decrease the amount of VOCs released, devices are built into fuel pumps and into vehicles themselves. Beginning in the 1990s, vapor recovery systems were incorporated into fuel station pumps. They're designed to trap the vapor within the vehicle, the nozzle, the hose, and the tank beneath the station, rather than allowing it to escape into the air. You may have noticed decals, such as this one, affixed to fuel pumps illustrating the effective use of the system. Beginning in 1998, federal regulations required that automakers incorporate vehicle-based vapor recovery systems for cars, trucks, and vans. The requirement was phased in over an 8-year period so that by 2006, all new vehicles were equipped with a vapor recovery system. For vehicles that run on diesel fuel rather than gasoline, requirements established in the early 2000s mandated the incorporation of a diesel exhaust fluid system. The fluid, added to a tank separate from the fuel tank, reacts with the nitrogen oxides present in the diesel exhaust. The chemical reaction results in nitrogen gas and water being released, two naturally occurring components of air. As seen in the previous video, catalytic converters are components installed in cars beginning in the 1970s. They are constructed to contain a combination of reactive metals that prevent the release of uncombusted hydrocarbons, carbon monoxide, and nitrogen oxides. Many factories and all fossil fuel burning power plants create air pollution. The types of pollution are the usual suspects: carbon dioxide, sulfur dioxide, nitrogen oxides, and, of course, particulate matter. In an effort to capture pollution before it escapes into the atmosphere, national and local governments have established requirements mandating the use of pollution sequestration technologies. These technologies include things such as baghouse filters, electrostatic precipitators, air scrubbers, and fluidized bed combustion in coal-fired power plants. Baghouse filters, or fabric filters, are a type of filtration device that allow gases to pass through them, but particulate matter is trapped. Certain types of baghouse filters can trap nearly 100% of the particulate matter emissions. As the filters accumulate more and more particulates, a mechanism that shakes the filters releases the trapped particulates, where it can be collected and then disposed of. Electrostatic precipitators use an electric charge to make particles clump together so they can be removed. Dirty air enters the precipitator and passes by a negatively charged electrode, which gives the particulates a negative charge. They continue on where they are exposed to positively charged electrodes, which attract the negative particulates to them. From time to time, the positively charged plates are deactivated, allowing the particulates to be removed, collected, and disposed of. An air scrubber uses a combination of water mist and air. Dirty air enters the scrubber and particulates are trapped in the small droplets of water. Just like rain can wash pollutants out of the air, the particulates in this system are carried down to a collection unit where the sludge can be collected and disposed of. One of the most common impurities in coal is sulfur. When coal is combusted, the sulfur is released into the atmosphere in the form of sulfur dioxide. A method for combusting coal called fluidized bed combustion works to prevent much of the sulfur dioxide from being emitted into the air. The process requires the heating of limestone, which is calcium carbonate, alongside the coal. As the sulfur is released from the combustion of coal in the form of sulfur dioxide, it reacts chemically with the calcium carbonate. The result is a solid substance called calcium sulfate. Because it is a solid, calcium sulfate is much more easily contained than the gaseous sulfur dioxide. And a bonus side effect is that the calcium sulfate can be used in a wide range of consumer products, having uses in dentistry, acting as a coagulant in tofu, and a component of building materials like stucco and drywall. That brings our look into these three topics to a close. Thanks for watching, and until next time, take care.